There are three ways to multiply a vector. You can perform a scalar multiplication, in which you multiply each component of the vector by a real number or a scalar. So for example, 3v. There we would just multiply each component in vector v by the number 3. You can also multiply vectors by vectors, and there's two different flavours of that: dot products and cross products. In this video we're only going to look at dot products, but we are going to see some nice way to use them, and we're also going to try out a few examples. Right, so we've got vector u, which is 7, 2, and vector v, which is 3, 6. And we've been asked to find the dot product of vectors u and v. So this here is the notation that we use, the u with a dot and then the v. The dot isn't right down on the ground on the line, it's sort of halfway up, if you see what I mean, the space between u and v, but that's the notation then for dot product. Now, when we calculate the dot product, we get an answer which is a scalar, or just a real number. So let's have a look at that. So we're just going to write the vectors out in their component form. So it's 7, 2 dot 3, 6. And to work this out, we're going to sum together the product of the horizontal components and the product of the vertical components. So first of all, we're going to do 7 times 3. And then we're going to add 2 times 6. Now that looks a little bit weird. 7.3 plus 2.6. Well, it doesn't mean 7.3 plus 2.6. It means 7 times 3, 2 times 3. And the times is the dot product times. We don't use the normal cross multiplication sign because that would confuse this sort of multiplication with vector cross multiplication. So sorry for the confusion there, but that's just a piece of notation that you're going to have to get used to, because that's what we use for dot products. So when you see this dot raised up off the ground a little bit, it means we're multiplying those two things together. So 7 times 3 is 21, 2 times 6 is 12. When we add those together, we get 33. So as we said, the dot product of two vectors, we just multiply each corresponding component together and then add up all those results. And the answer that we get is just a number, a scalar. So let's summarise that then. The dot product of two vectors is the sum of the products of the corresponding components. So we multiplied the x components together, and then we added the product of the y components in this case. So we were working with a two-dimensional example, but that can also be scaled up to 3 or 4 or any dimensional that we like. Now obviously vectors u and v have to have the same number of dimensions as each other, but you know, we can have 1, 2, 3, 4, as many as we like here, up to n dimensions in each. And all we're going to do is multiply together the corresponding components. So that's u1 times v1, and that's just a scalar, a real number result. Then u2 times v2. Then we're going to add u3 times v3, and all of the others, u4, v4, u5, v5, and so on, all the way up to un times vn. And so we're just multiplying a number by a number, a number by a number, a number by a number, and so on, and adding them all together. The answer we're going to get is just a real number, or a scalar. So that's the process, expanded up to n dimensions, and as many dimensions as we like. Now, while we're here, let's just quickly revisit magnitudes of vectors and just bring something else into play. So here we've got vector AB, which has got an x component of 5 and a y component of 12. Now you should remember that if we wanted to work out the magnitude of vector AB, what we need to do is use a bit of Pythagorean theorem and work out the square root of 5 squared plus 12 squared. Which, for those of you who are curious about it, the answer comes out to be 13. But that's kind of irrelevant for what I'm going to say. I just want to take a quick look inside this square root here, inside this radical here, and look at that expression that we've got. Now, just imagine that we did vector AB dot vector AB. That would be 512 dot 512. So we're going to just multiply the corresponding components together and add those results. So that's going to be 5 times 5, add 12 times 12. which gives us 5 squared plus 12 squared. So actually what we've got here is the same as the thing that we've got here. So what's inside that square root there is AB dot AB. So the magnitude of vector AB is just the square root of AB dot AB. And we've done that on a 2-dimensional example, but that also works on a 3-dimensional, 4-dimensional, as many dimensions as we like. So that's quite a nice, simple, useful result that we can use. So all it means is we're taking the square of each component and then adding them all together and then putting that inside the square root. Okay, so now we've met dot products and we've tried one out, and don't worry, we're going to practice them a little bit more in a moment. Here's another useful result that will help us to find the angle between two vectors. If we've got two vectors, u and v, they could be 2-dimensional, could be 3-dimensional, could be any dimensional, as we said before. Cos of the angle between them is the vector u divided by the magnitude of u, so that's the unit vector in the direction of vector u, dot the unit vector of v in the direction of vector v. And so theta, is obviously, as we said, is the angle between those two vectors. So this is a great result. We can rearrange that. So obviously if cos theta equals all that stuff, then theta is equal to cos to the minus 1 of all that stuff. So that's just another slight rearrangement of the formula. So if we find the dot product of the unit vectors in the directions of u and v, it gives us the cosine of the angle between them. And from that we can find the angle between them. So let's take a look at a couple of examples of that in action. Right, so we're given that vector u is 4, 1 and vector v in its component form is 2, 5. We've just got to do two things. 1, find the dot product of those two vectors, and 2, find the angle between them. So first, let's just quickly do a sketch of that situation. So I've got vector u is 4, 1, vector v is 2, 5, looks roughly like that. And what we're also trying to find is this angle theta, which is the angle between the two vectors. Okay, so let's go ahead and do that. So to find the dot product of the two vectors, remember we're just going to multiply the x components together and add that to the product of the y components. So that's 4 times 2 and 1 times 5, which is 8 plus 5, which is equal to 13. So that part of the question was pretty quick. The dot product of u and v is 13. Now to find the angle between them, we know that the cos of the angle between them is the dot product of the unit vectors in the direction u and v. And to find the unit vectors, we take vector u and we divide it by the magnitude of itself, and we take the vector v and we divide it by the magnitude of itself. So let's write some numbers in. So for vector u, which was 4, 1, to work out the magnitude of that, I'm going to do the square root of 4 squared plus 1 squared. So take each of those components, square them, add the result together, take the square root of that. So that's basically our Pythagorean theorem thing that we were doing. And let's do the same again for v. And because the components of v were 2 and 5, it's just 1 over 2 squared plus 5 squared, lots of vector v. So all this means is we've got each component of u divided by the magnitude, and then we'll have each component of v divided by its magnitude as well. So 4 squared plus 1 squared, that's 16 plus 1, so we've got root 17 for that one. And then we're just dividing the x component by root 17 and the y component by root 17. So let's do the same for v. 2 squared is 4, 5 squared is 25, so we've got 1 over root 29. And dividing each the x and the y components by root 29, that vector now becomes 2 over root 29, 5 over root 29. So doing the dot product, we're going to be multiplying this term by this term, and we're going to be multiplying this term by this term and adding the results together. So cos theta then is equal to 4 over root 17 times 2 over root 29 plus 1 over root 17 times 5 over root 29. And 4 times 2 is 8, and 17 times 29 is 493, so we've got 8 over root 493. 1 lot of 5 is 5, so that's 5 over root 493. 8 and 5 makes 13. So cos theta is equal to 13 over root 493. So we now just need to do the cos inverse of that. So cos to the minus 1 of 13 over root 493, which is 54.2 to 1 decimal place. So that's our answer. Well, that's our answer in degrees to 1 decimal place. So this angle here is 54.2 degrees to 1 decimal place. So that whole kind of part B there hinged on the fact that the cosine of the angle between the vectors is equal to the dot product of the unit vectors in the directions of u and v. And to work out a unit vector, you take your vector and divide it by the length of itself. So it has a length of 1. We followed that through, did the inverse cos, and we got our final answer. Okay, one more example then. Find the angle between vectors u, which is 3, negative 2, and v, which is negative 5, negative 3. So let's just do a quick sketch to see what this looks like. So u is 3, negative 2, and v is negative 5, negative 3, and the angle between them is going to be this angle here, hopefully, and we'll call that theta. Okay, so we don't need to work out the dot product of u and v to start off with. That was just in the previous question. All this is asking for is for us to use the result that cos theta is equal to the dot product of the unit vectors in the directions of u and v. So in fact I'm going to rearrange that and do theta equals cos to the minus 1 of all that. So let's just write that down. So it's always a good idea to write down the result that you're starting off with, so the thing that's going to drive your calculation. Right, let's do a bit of substituting in now. So we know how to work out the magnitude of u. It's just going to be the square root of 3 squared times negative 2 squared. And let's just write that bit out now. And the same again for vector v. So you can already see this starts to look a little bit clumsy because I've rearranged this into the theta equals cos to the minus 1. I'm writing all these big brackets out every time. So you can kind of make your decision about whether you use this form straight away or whether you use the previous form that I just used and then do your conversion at the end to cos to the minus 1. But let's plow on with the exercise anyway. So let's evaluate each of those terms. Okay, so 3 squared plus negative 2 squared is 13. So the u vector becomes 3 over root 13, negative 2 over root 13. And then moving on to the v vector, 5 squared plus 3 squared gives us 34. So the v components are minus 5 over root 34 and minus 3 over root 34. So we've just got to do the dot product of those. So that's going to be this component times this component plus this component times this component, which gives us this. And now I've got 3 over root 13 times negative 5 over root 34, and I've got negative 2 times negative 3 over root 13 times root 34. So that gives us negative 15 over root 442 plus 6 over root 442. Add those two together and I've got minus 9 over root 442. So if I get my calculator out and do the inverse cos of 9 over root 442, that gives me an angle of 115.3 degrees to 1 decimal place. So there it is, that's my answer. Now let's just quickly check back to the diagram just to make sure that that all makes sense. And it has given me an angle of 115 degrees, which fits in with this angle. It hasn't given me this angle around the outside. Sometimes you just need to check exactly which angle it's calculated for you. So hopefully that's nice and clear on that. Okay, so let's just do a quick summary of what we've looked at in this video. The dot product of two vectors, we just take each of the corresponding components of the vectors and multiply them together. So u dot v, we've got u1 v1 plus u2 v2 plus u3 v3 all the way up to un vn. So that's a simple case as we've seen in our example if we've got a two-dimensional example, but it can be scaled up to any dimensions that we want. And the result is just a number, a real number, a scalar. And also the dot product of the unit vectors in the directions of two vectors gives us the cosine of the angle between them, which enables us to work out what the angle between two vectors is. Very, very useful. Okay, that's it for now.